working on periodic table review since Canvas is down. This is going over everything that we went over last week. Okay, the test over this is gonna be on Wednesday. So tomorrow we'll be just doing more review. This is just kind of in place of what we were going to do today. All right, so the first thing that we talked about last week was just the periodic table and where things are located. Okay, so if I'm talking about something that's up and down, all right, we're gonna call these groups or families. All right, some of these families have specific names. We'll go over that on another periodic table. All right, and if I'm talking about something that is, we're going left to right, do y'all remember what we call that? Periods, yes ma'am. Yes, sir.
Do we draw all three periodic tables?
Eventually you will, yes. If you want to do just one at a time, you can start with this one. Yeah, eventually we'll do all three, but if you want to start with just one, we'll label, take notes, and then move to the next one. All right. On the periodic table, you see something that looks like this. Okay, the stair step line. Granted, I'm not an artist, but you can at least get the picture. Okay. If an element is touching this stair step line, we call them metalloids. Okay. The only two exceptions, how do we spell that? The exceptions are aluminum and polonium. They touch the staircase line, but they are metals. All right, to the left of the staircase are the metals. To the right of the staircase are the nonmetals. And things that you'll need to know for your test but are in your notes are like metals are shiny, conduct electricity, nonmetals are dull and break easily, and metalloids are a little bit of both. They act like both. So there's more specific details of that in your notes, but the main thing I want you to remember today is where they're located on the periodic table. Okay, so most of the periodic table's metals, then you hit your metalloids on the staircase, and then to the right we have the nonmetals. Okay, so this was Monday. Then on Tuesday we started talking about the families. Okay. All right, so there was 4 families that we talked about. And I'll give you all a second if you haven't drawn this periodic table yet. Okay, so the 4 families that we talked about, this first one is group 1A. If you look at the top of your periodic table, you see where it says 1A. All right, and this is the alkali metals, AlKali metals. All right, this group only has 1 valence electron, so like lithium looks like, whoa, sorry, trying to figure out what I'm drawing. So lithium has 2, 3 electrons total, okay? But it only has 1 electron in the outermost orbital. Okay, so that's 1 valence electron, okay? And remember, valence electron is electrons in the outermost orbital. And it's easier for lithium to get rid of one electron than it is to go around and find 7 electrons, because that would take a lot of energy and a lot of time. So when it loses this electron, it's going to have a positive 1 charge, right? Remember that electrons are negative, okay? So when you lose the negative charge, you now have more positive protons than you do electrons. So that's why it's a positive 1 charge, okay? The next family that we have is the alkaline. Earth metals. Okay. ALK, ALINE, earth metals. And this is group 2A, so the next group over. All right, and so the very first of these is beryllium. Okay, so like lithium has 2 electrons in the first orbital, and then unlike lithium, this one has 2 valence electrons. Again, it's easier to lose 2 electrons than it is to try to find 6 electrons, okay? Elements are lazy, they want to do whatever easiest to lose 2. So when they lose 2 electrons, they're going to have a positive 2 charge, okay? So positive 2, negative, or positive 1. All right, so when we're saying charges, this is where we're getting the charges from. All right, and then we're going to jump over the transition metals, over the carbon group, the oxygen group, and we're going to jump to group 7A. All right, this is called the halogens. All right, with halogens, the very first element is fluorine. So 2 electrons on the first one. Then the second group, or the second orbital, because it's group 7A, is going to have 7 valence electrons. If you haven't noticed yet, whatever the group number is, that's how many valence electrons it has. So 1, 2, 3, 4, 5, 6, 7. So for fluorine, it's easier to find 1 electron than I'll make that look a little bit better. Okay, it's easier to find 1 electron than it is to lose 7 electrons. Okay, so when it does that, when it gets the extra electron, now it has more electrons, so it's going to have a negative 1 charge. Okay, so halogens have a negative 1 charge. All right, and the last one, this is group 8A. Okay, this is the noble gases. All right, they're just noble gas. All right, the noble gases, except for helium, already have 8 electrons in the outermost orbital, and that's what the octet rule wants us to get, is the 8 valence electrons. Okay, so this is perfect. It has no charge. Okay, it doesn't gain electrons, it doesn't lose electrons, it's happy as it is.
Is that a reason why a lot of those gases are chemically inert?
Is that why?
Yeah.
Yes. Yes, that is why they don't mix with other chemicals, is because they don't want to have anything to do with them. They've got their 8, they're good to go. Good question. All right. Let's see, other terms that you might see, okay, is the metals, okay? So something's a metal, all right, over here. Metals are called cations, and it's because they're positive. And nonmetals, okay, like the halogens, are called anions. And that's because they're negative. Okay, so just terms that you'll see, and there will be a heavy vocabulary section on the test. So this is terms that you want to make sure you know. And you want to make sure you know the family names as well. All right, everybody good and caught up right now? Okay, if you haven't already, go ahead and draw this last periodic table. All right, of the three things that we talked about last week, where the elements are on the periodic table, where the families are, and then the trends. Trends was the hardest one to understand, okay? So this is gonna be kind of a extra review for the trends as well. All right, the first trend that we're gonna talk about is atomic radius.
I think the other reason why this one's mostly hard for us to understand is that everything else we've kind of been going over since 7th grade.
Yes, and so this is the first new topic, okay? So with the atomic radius, this is talking about the overall size of a neutral atom. Alright, so again, the overall size of a neutral atom. So no electrons have been lost, no electrons have been gained. This is just the size of the atom as it's found. Okay? When we're looking at the periodic table, alright, so here we have hydrogen, then we have lithium, then we have sodium, and on down the list for the alkali metals. Okay? Every time we go down the list, so hydrogen has one electron in the first orbital, that's it. Lithium has a full first shell, but only one electron in the second shell. All right, and then sodium has the first shell and the second shell. 1, 2, 3, 4, 5, 6, 7. Okay, first shell and the second shell are full, but the third shell only has one valence electron. Right. If I were to keep going, the same thing's gonna happen, okay? Whenever I go to the next one, now the third shell will be full, but the fourth shell will only have one valence electron. Okay? So as we're going down, what's happening to the atom? Is it getting bigger or smaller?
There.
Okay? So with the atomic radius, the trend is as you're going down a family, you are increasing in size. Okay, now this next part's gonna seem kind of weird. Okay, so I'm gonna do lithium. Next to lithium is beryllium. Okay, so beryllium has 2, and then it has 2 valence electrons here. Okay, the way that it goes is, let's see, beryllium, then it's boron, and then carbon. The picture here is not going to do the justice that it deserves, but I'll explain myself, okay? So as we're going across a period, we're adding 1 electron to the valence electrons, correct? okay? When that happens, that's, the more valence electrons you have, the more attracted you are to the center of the atom, okay? So as, again, my pictures aren't doing justice, but what it should look like is that they're getting smaller as you go across. Because again, as we're adding the valence electrons, that's getting more attracted to the nucleus, so the atoms themselves are getting smaller. All right, so this trend is as you go left to right, it is decreasing. All right, some good news to go with this is that when it comes to ionic radius, okay, ionic radius is the overall size of a charged atom the trend follows the same pattern, okay? Same pattern, so increasing, decreasing. Okay, because now they're charged, so it does, like, when this loses, when lithium loses its valence electron, alright, the atom is smaller than it originally was, okay? But it's still gonna be bigger than beryllium when beryllium loses its 2 electrons. Okay, so the trend, like, this one's neutral, this one's charged, but it's still decreasing as you go left to right, it's still increasing as you go top to bottom. When it comes to the test on Wednesday, the way you're gonna see some of these questions asked is, like, it's gonna say, which one's bigger, aluminum or phosphorus, okay? So we'll say larger atomic radius. Okay, so this is the question, which one has a larger atomic radius out of aluminum or phosphorus? When you look on the periodic table, it looks like this. Okay? So when we look at it like this, if we know that it's decreasing as we go left to right, then that means that aluminum would be the larger of the 2. And I'm not going to try to trick you guys on the test, all right? For the test, it's either going to be in the same period or it's going to be in the same family. All right, so like here, which one's larger out of lithium and sodium? The answer would be sodium because it's further down on the list. All right. So I'm gonna erase this real quick just so I can have some more board space. We're gonna talk about the other 2 trends and then we'll be done. All right, so y'all can use the same periodic table. Again, I'm just doing this so I can have more space. Okay, so the last 2 trends that we're talking about are electronegativity and ionization energy. All right, remember that I said vocab was going to be a big part of the test. All right, so make sure that you know that electronegativity is talking about the ability to attract electrons for bonding. And ionization energy is the energy required to remove an electron. Okay. So when it comes to electronegativity and ionization energy, I'm going to mostly be talking about these two elements. Fluorine, which is actually, this is the noble gases, so fluorine is right here. I'm not really going to be talking about noble gases with either of these. Okay, we're just talking about fluorine and francium. Okay, so electronegativity is the ability to attract electrons for bonding. Ionization energy, energy required to remove an electron. These are the same but opposite as far as definitions go. Fluorine has a -1 charge. That means it's looking for, or it has an extra electron, so it wants one more electron, okay? If I were to draw fluorine, okay, so 2, and then because it's in group 7A, it would have 7 valence electrons. Okay, so it's looking for that one more electron. But this right here is the smallest, except for hydrogen and helium, it's the smallest atom. These 7 valence electrons are super close to the nucleus, so they have a really strong pull to the nucleus. So for fluorine, this is the easiest, okay, or we'll say the most ability to attract electrons, so it's the most electronegative element. Alright, because it's so small, because everything's so close to the nucleus, it's very easy for fluorine to steal an electron to get the octet hole. Okay? It has, like, if fluorine was in a tug of war with any element, it would win every single time. That's how strong it is. Alright? And it's also the smallest element, which I've already mentioned. Think about toothpaste. What's the #1 ingredient in most toothpastes? Paste. Fluorine. Okay? They use that because throughout the day, as you're eating, your teeth get scratched. Alright, so when you brush your teeth and you use fluorine, the fluorine fills the scratches that happen in your teeth to keep your teeth healthier. Alright, that's why there's fluorine in drinking water. Okay? Like cities put fluorine in the drinking water to help keep teeth healthier. If you ever go to a city that does not put fluorine in the drinking water, they tend to have more cavities per citizen than places with fluorine in the water. Okay? Let's see. And as far as fluorine with ionization energy, it's the energy required to remove an electron. Fluorine has 7 valence electrons. It does not want to lose any electrons. So this would take an enormous amount of energy to steal an electron from it. Okay, so this has very high ionization energy because it wants to keep all of its electrons. All right, so that's the story of fluorine, okay? Big, strong, the mountain from the Game of Thrones, okay? Who I think won the strongest man on earth competition. I'd have to look that up. All right, and then we have little francium in the corner, okay? And by little francium, I mean big francium, because francium is the biggest element, all right? It's in the 7th group, so francium, 1, 2, 3, 4, 5, 6, 7, okay? Huge element, all right? And it has one valence electron. Do you think this one valence electron has a lot of attraction to the nucleus? Okay. No, it doesn't. Look how far away it is from the nucleus, all right? So it's gonna be, let's see, the ability, so as far as electronegativity goes, the ability to attract electrons for bonding, this isn't attracting anything, all right? It's too large. There's no attraction to the nucleus, all right? Ionization energy required to remove an electron, it's basically giving it away, all right? So the ionization energy needed to remove the electron, it's handing it to whoever wants it. So like fluorine wants it, here you go, all right? No energy needed, all right? So this is the weakest element. I'm gonna do a little sad face, okay? Weakest. If this guy, francium, got in a tug of war with anybody, it will lose every single time, okay? So when we're looking at the arrows like we did with the atomic radius and ionic radius, okay, for electronegativity and ionization energy, as we get closer to francium, this is decreasing in energy. It's easier and easier to get rid of electrons, okay, the further down we go. Again, it's because we're adding more levels, it's getting larger and larger, okay? Then as we get closer to fluorine, this is increasing in energy. The closer you are to fluorine, the stronger you are, okay? The least likely you are to get rid of an electron, but the more likely you are to be able to attract electrons for bonding. Okay? So when it comes to the trends, my biggest suggestion, okay, is if you can remember that the atomic radius is increasing as it's going down because it's getting larger, okay? That means this arrow is the opposite. You're always gonna have increasing and decreasing with the trends. So if we know that this is increasing going down, then it has to be decreasing as it goes left to right, okay? And this is the same for ionic radius. All right, then when it comes to electronegativity, and ionization energy, okay, if you know that atomic radius and ionic radius is increasing down, decreasing left to right, electronegativity and ionization energy is the exact opposite. Okay, so this time it's decreasing going down, and it's increasing going left to right. Okay, and the questions will be asked the same, like out of aluminum and phosphorus, which one has more ionization energy? Okay, in this case it would be phosphorus has more ionization energy because it's increasing going left to right. All right, and then say out of lithium and sodium, which one has more electronegativity? Well, this time it's going to be lithium because we know it's decreasing as it goes down. All right, so if you know these terms and you understand this kind of questions, that's going to be a big part of the test. All right, make sure you also know the families and just you can identify if something's a metal or a non-metal. But if you get this today, then that's really going to help you for the test on Wednesday. All right, so